Today I'm going to be going over my MATLAB script that I call the Integrated Design Tool, or IDT for short. So this is a script-based code that has a main function here called master file, and this is going to call all of these other functions here, some of which are sub-functions of themselves, and some are called multiple times. So I'm going to walk you through where in the code that these are called, what each one does, the input parameters, as well as what sort of outputs you can expect. And then after I walk through the structure of the code, the functions in it, and what it can do, I will do a demonstration for a vehicle to show the plots that are generated and what sort of results that you get. All right, so starting off, the first section of the code is where you define your initial parameters. So these are the sort of things that you want to be able to change on subsequent iterations, especially between different types of vehicles. So this is my toggle switch section where it's more general of the type of geometry or features that you'd see on the aircraft, for instance, whether it's manned or unmanned. So this is called throughout the code numerous times where you'll be seeing, if it's an unmanned aircraft, you might have an increase in avionics weight or a reduction in furnishing weight or the elimination of the crew station. So those features come into play later, and it will take these initial switches and use them as if-else statements in the code. So that's why I have them defined as simply numeric scalars, and you'll see that later on. One important thing to note as well is that these mission parameters and basic parameters can be changed. So that's why I put them in the initial section. So for instance, the loiter Mach number might change based on an optimization later on after a number of subsequent iterations. It might be found that your maximum L over D occurs at a Mach 0.3 at 20,000 feet. So in your concept of operations, that would be your ideal Mach number to loiter at. So we could go into the code, and when we're running our next iteration, we know that the vehicle will be similar to the one that we designed before, so we'd be able to change that loiter number to something closer to the expected optimal value, and then that should allow us to approach the minimal weight of the aircraft. So going through here, another interesting parameter to note is this ATE factor. So this is an adjustment factor for engine technologies. Basically, it's given by Raymer as an estimate to allow you to take a rubber engine and scale it for future technologies. As you know, engines will always continue to improve in terms of exit combustor temperature as well as the size of them. So that will have a direct impact on the fuel consumption as well as the weight and engine face diameter as well as potentially the length. So this factor is used later on to help scale our rubber engine to account for something that would be indicative of an advanced engine for an aircraft like this. Going on, we see that we have wing parameters and then tail parameters for either a V-tail or a standard or T-tail. So if we come back up here to the toggle switches, you can see that we have a tail type, which allows for different types of tails to be put on the aircraft, whether you're going with your standard tail that you see on about 75% of aircraft flying today, something with a little less drag but maybe a little less maneuverability, and then a T-tail, which I don't think has been done on a fighter for a while now, maybe since the F-104, but I put that option in there just in case one of the designs that I come up with ended up utilizing that type of geometry. So these are the very basic parameters that you kind of need to pick for your wings and tails, such as just the aspect ratio, taper ratio, and then the leading edge sweep. Later on, we can fully define the geometry once we get the area, which we will get after we get wing loading and thrust to weight. And we can do the same with the tail. And then we have tail volume coefficients and moment arms. Once again, these are just estimates from Raymer, which will allow you to properly size the tail for this class of aircraft. Going on, we have profiles for the mission. So here we can change our payload weight as well as the best Mach numbers for the different mission segments, such as cruise, and then also combat, and how fast we want to accelerate to at the end of our supersonic dash into combat here. So after we have defined all of our initial parameters, we can move on and calculate the initial weight of the aircraft. So it will take a large number of these and call this function initial weight estimate, which we can go to now. So initial weight estimate will take in things like whether or not the aircraft is unmanned, how high it will be flying at, the type of payload that it needs to take in, and also the Mach numbers that they are expecting to fly at. And here I have a correction. So if it's unmanned, there's a correction for the empty weight fraction. It'll go down around 4.5%, and that was estimated. You can see that from an earlier work I have. And then I also have a correction for the composite. So this aircraft is assumed to be made of fully composite materials in the main sections, such as the air induction system, fuselage, wings, and tails. So that will result in about a 5% to 8% reduction in the empty weight. And then for reserves, so 5% reserve plus 1% trapped fuel leads to a 1.06 empty weight fraction. I can then toggle my atmosphere function, which I'll show you here. This is just a standard atmosphere function. So you put in the height, and on a standard day, it will give you the speed of sound, the kinematic viscosity, and the density of the air based on its height, which is very useful for when we're determining our dynamic pressure as well as our Mach number. So going on, we can call that based on the cruise height that we input in, and it will give us the parameters that we need, such as our speed of sound. So the very first thing that we do is set up an iterative loop where we guess the gross weight and calculate a new weight based on the design mission and see if they are equal. And if not, then we can converge and come back to it. And we can do this automatically with the loop. So by the end of it, we will have something that converges and then thus, according to the code, meets the mission requirements and allows you to have a complete aircraft. So then from that, we can pull the empty weight, the maximum gross weight, and then the fuel weight. So going through, we just have the standard segments. These are all seen in the concept of operations. I think this first section here, yes, mission 1 is air to air. We should have a mission 2 with air to ground. So these are different segments for different parts of the mission. Things like the combat, acceleration, and then obviously cruise, loiter, and landing. So at the end here, we will calculate like the fuel fraction, plug in the reserves, do the calculation for the payload and the crew, and then it will end up with the empty weight, the takeoff weight, and the fuel weight, which will be then outputted back into our main function as 6 different variables. So they're going to be 3 for the air-to-air mission, and then 3 for the air-to-ground mission. So going back to the master file now, after these are outputted, these will be printed out to the user so they can look at them and see whether or not the takeoff weight for the air-to-air and the takeoff weight for the air-to-ground are roughly equivalent, because we know that we need both the empty weight and the takeoff weight to be similar. The main difference here is going to be the payload weight and also the type of mission that it's performing. So that allows for some iteration of the user to vary the payload to allow those to converge. So for instance, if we said that the payload for the air-to-ground was going to be 4,000 pounds and the payload for the air-to-air were to be 1,800 pounds, you could arrive at a similar solution. And then I have this if statement here. Basically, if they're not equal, what it allows you to do is input a new weight, and it will recalculate this. It's on a while loop, so it'll keep going until the user is satisfied. And that will allow you to converge it manually by adjusting the payload in specific increments. For instance, missiles, like I have tabulated values of like the AIM-9 and AIM-120 missile weights, so I could incrementally add or subtract those, or the GBU-27s for the air-to-ground, to determine a realistic change in payload weight rather than just some sort of decimal number that an optimization loop would most likely converge on as the optimal solution. So that is why that was done manually. Moving forward, once we have that initial weight, we can then calculate our wing loading and thrust weight. I have another function here. The maximum gross takeoff weight for this was assumed to just be the maximum between the takeoff of the air-to-air or the air-to-ground. Obviously, if we do the maximum here, then the other solution should be converged as well. Going here, we can look that we put in a lot of parameters here. Some of these were from the initial parameters, such as like the aspect ratio of the wing or an initial guess at the parasitic drag coefficient. So now let's hop over to the wing loading and thrust to weight function. So the first thing that we do is we're going to guess the thrust to weight by using a semi-empirical formula that is just a function of our maximum Mach number for a fighter jet aircraft. I think that was 1.8, so we would plug that in and it would calculate an initial guess. From there, we can look at the different wing loading requirements. So we'll have stall, takeoff distance, landing, cruise, loiter. For this aircraft, the critical factor is normally the instantaneous turn wing loading at 25 degrees per second. That's quite a restraining requirement. So that one will normally dictate it. So once it calculates all of these, it will print them all out, and then once again it goes to calculate the thrust to weight for combat, and then it can adjust that back using fuel fractions back to the thrust over weight for takeoff, and then it will print that out as what is needed to satisfy the design conditions, and then ask the user once again what they would like to pick. So in this part of the code, it's not a calculation and then an instant selection, but rather a calculation. The results are displayed to the user, and then they're allowed to pick it based on the design space. So if you were to plot this, there'd be an intersection of the points that would most likely be a minimum, but that might not likely be what you want. If for instance, the wing loading, you wanted a little bit higher to say allow for more cruise or more efficient cruise, or if you wanted the thrust to weight to be higher, you can always have that. Just a larger engine might not necessarily be optimal, but at this point, it's hard to know. So you have to use more refined methods later to determine the optimal wing loading and thrust to weight. So at the end of this, the outputs are going to be your thrust to weight and your wing loading. It'll come back out into the master file here, multiplied. The inverse of the wing loading will be multiplied by the maximum takeoff weight, and then the thrust to weight will be multiplied by the same value to determine our reference wing area and then our maximum engine thrust at sea level needed for takeoff. So now that we have the reference wing area, we can calculate the general aircraft layout. That's starting with things like the root and tip chords, the aerodynamic center, the sweep line of maximum thickness, the quarter chord sweep line, the wingspan, and other parameters like that. For the tail, we have a toggle here, so it depends if the tail is a V-tail or a standard tail like we had seen before. So here comes that initial toggle switch. Like I said, they're all throughout the code, and we'll see them as we go on. So let's focus on for right now. We'll look at this is the V-tail section. So, oh no, I'm sorry, this is the standard tail section, and this is going to be the V-tail section. So for the standard tail section, you're going to calculate the same parameters, but you're going to do it twice, one for the vertical tail, one for the horizontal tail. No main difference between this and the wing section, since the tails are approximated as small wings, which is fairly standard and a good approximation. Moving forward for the V-tail, what's fairly interesting is, of course, we can calculate the dihedral angle of that V-tail, and also the overall parameters are going to be based on the area of an estimate for the vertical and horizontal tail combined. So, NASA studies have shown that in order to gain the maximum effect of a V-tail, it needs to be the same wetted area or same reference area as a standard tail. So we can get that by adding the vertical and horizontal tail, and then finding the dihedral angle of that and setting them up as the V based on that value there. And then at the end of this, once we calculate all of these values, we can estimate the wetted area of the tail, which will be seen right here and also right here. And that will come into play later on when we're looking at the parasitic drag buildup in the aerodynamic section. So moving forward, we can estimate the fuselage length, once again using sort of a semi-empirical formula that takes in the maximum gross takeoff weight and also the type of aircraft, in this case a fighter. So one thing that I did is, if the aircraft is unmanned, you're going to have a general reduction in the fuselage length because of the elimination of the crew station. This value, 7.5 feet, came from Nikolai's Fundamentals of Aircraft Design. That was the value that he estimated for an unmanned fighter jet, the space that you could save due to a lack of a crew station. So now, once again, this is just an estimate. So when you're doing your very first drawing, it's not going to be this exact value. So the next part of the code is estimating, or the estimated fuselage length based on the as drawn length. So if we come over here, we can see, so once we get the wing geometry and the tail geometry, we know the moment arm. We can place both of these on the paper, and then we can also place in the engine because we know generally where it's going to be in this type of aircraft, back and embedded. And then from there we can sort of sketch in the fuselage, generally based on the avionics volume, where the pilot would be if it was a manned aircraft. This is the unmanned layout, and then also how much fuel and payload needs to be internal to this body. So from there we can, we know each square is 2 feet by 2 feet. We can count from here to here. Ends up being about 43 feet for this iteration. We come back here. In the prompt, we can put in the as drawn length, the maximum cross-sectional area, top-down area, side area, and then the maximum diameter. So these are all things that we don't necessarily know right away, but once we draw the aircraft, then we can calculate it by sort of counting the squares and estimating based on the diameter that we see and the shape of it, whether it's an oval in nature or a pure circular, maybe here where you have your radome. So coming back here, once we calculate all of those, or sorry, once those are inputted, we can calculate the wetted area of the fuselage, which once again will be very important when we are determining the aero component drag buildup. So moving on, we can go to the engine sizing. This is going to use a rubber engine, basically based on the maximum thrust of a reference engine from Raymer. We have our scale factor here, which is going to be the ratio between our sea level thrust and then the sea level thrust of this rubber engine. And then the scale factor can be put into these equations to determine the length of the engine face diameter, and then the weight of the engine. So what I have here also is a first order statistical estimate based on the maximum Mach number, the thrust, and I believe the bypass ratio. So these are going to be compared, and then the greater of the two values will be picked, just to be safe, sort of a more conservative estimate of the engine. One thing to note is that these are for an advanced engine, where these are for a standard engine. So these have all been applied the advanced technology engine factor, or the 0.8. For some reason it's hard coded here, but you could obviously just put the ATE factor, and then if you wanted to vary it to say only 90% reduction, or a 10% reduction, put it at 0.9. You could do that very easily back in your initial estimate. So it will take the maximum of those two values, so whichever's larger, and then that is going to be your length, diameter, and your weight. These are also initial estimates for your specific fuel consumption and your thrust at cruise, but I ended up not using these because I found that they were not very good estimates. I have a better method later on where we pull a reference engine from Nikolai, and I'll go over that in a little bit. So after we go through the engine, the next thing that we want to look at, of course, is the inlet. So there's a lot of different inlet configurations, not only in position, number, but also whether or not it's going to be a pitot inlet, external or internal, or mixed compression inlet. So the first thing that we kind of look at is, how big does the inlet need to be? So the capture area is going to be based on our design Mach number. And there's a nice figure in Raymer that allows us to go and look and say, based on our design Mach number, what is the capture area? And then in the prompt, I give the page number so the user can quickly reference that work and put in the value. And the same thing for the mass flow at the design Mach number. So now that we know the capture area and the mass flow, we can scale. That's for, sorry, this one right here is for a reference engine. So we have to use our scale factor to scale back what the actual capture area and mass flow needs to be. Going on from there, we can put in the diameter of the engine face, which will allow us to better size the inlet, the capture area needed, and then it will output that capture area and diameter, and then you can say, based on that, what is your desired inlet width and also your desired inlet height. So for instance, if you have a inlet of about, let's say, 4 square feet, you could say you wanted 2 square inlets of 1.5 by 1.5, and that should be good. Moving on, it prompts you to ask, where are the inlets? So are they on the fuselage, or are they going to be elsewhere in the aircraft? I think for most fighter jets, they're going to be on the fuselage, whether that's a chin inlet or on the sides. But I put that in there just in case that I ended up with a design where the inlets were elsewhere on the body. And that's going to be used later to determine certain factors for the weight estimation. And that's the same for the inlet duct shape. That's for weight estimation. So 2 flat sides, it's going to be an inlet similar to like the F-15, where you're going to have an external compression inlet. For only 1 flat side, you might have a more curved inlet like the F-16, where that's going to be your standard pitot inlet. Moving on, we have our boundary layer diverter, very important, especially at high supersonic speeds. So we need to determine the size of that to make sure it's adequate, as well as what is the wetted area of that. So we need to know basically how far back the inlet face is going to be from the nose of our aircraft, and that will allow us to estimate the size of the diverter, the height, the length, and then from there we can determine the wetted area. The landing gear is going to be a function. This is going to be outputted so the user can go and select the landing gear from like a Goodyear tire chart. Basically, it'll calculate your maximum takeoff weight by using our maximum design payload of 14,000 pound ordnance, along with our maximum empty weight and fuel weight. So this is sort of what's the maximum weight that we're ever going to see the aircraft be at. That's kind of over the design weight, and then we will come up with our max takeoff weight. From there, we can use that to size the landing gear. The control surfaces are going to be estimated as about 30% of the surface area relative to whatever surface they're on. So that would be, say, the ailerons are going to be 30% of the wing, and then the rudder vaders, or the rudders and elevators separately, if you're a standard tail, are going to be about 30% as well. So then a next large component that we need to calculate is the fuel. So we're going to be using Jet A fuel for this engine, which has a density of 6.7 pounds per gallon on a standard sea level day. From that, we know basically the weight of the fuel because we got that when we did the initial sizing. From there, we can figure out the volume that it's going to take up. Then what we need to do is determine the volume between the wing and then the fuselage, because it needs to be distributed in 2 different tanks. In the wing, it's going to be a self-sealing tank, so if it sustains combat damage, it won't be a critical loss of the aircraft. In the fuselage, it will be a conformal tank, and that's just to save weight. So from there, we can go back to our drawing and sort of count the squares. So here, the shaded area is going to be estimated where we'd be able to fit in fuel. Now, obviously, when you have a self-sealing bladder tank, as well as you're going to have a lot of wing spars in there, it's going to be a reduction in the usable volume. Those are all accounted for in here, and you ended up with a certain number for this aircraft, which can obviously be changed for any other iterations. And then that will allow you to calculate the weight of the fuel in the wing and the weight of the fuel in the tank. And then you can determine also the number of gallons in each by just dividing by the density. So we've just covered the entire layout of the aircraft. We can go back here and kind of see what we've all done. Now we can move on. Oh, I went a little too far. Now we can move on to the aerodynamics. So now that we have the layout configured, we need to figure out the propulsion, the aerodynamics, the weights, the performance, the costs. We can look at the structures a little bit, although this tool doesn't cover structures or stability. The reason for that is that stability and control, this is going to be a relaxed stability fighter that will use a 6 degree of freedom, or a three axis flight control computer. So it's going to be, as long as you have adequate control surfaces and large enough tails, then the controllability and the stability of the aircraft is less vital than, say, a transport aircraft that's held to different standards basically. And then for the structures, it's a little bit hard early on to do any meaningful calculations other than selecting the materials and kind of doing a general layout of what sort of structures you want to use, whether that's rib spar, multi-spar in the wing, or what type of longerons and rings you want to use in the fuselage or around the engine for the wing box. So those are all laid out in the report, but in terms of the tool, there's not really much to calculate, so we've omitted that. All right, so moving on with the aerodynamics, the first thing to determine is what area of our wing is covered by the fuselage. That's going to be useful for turning our reference wing area into our actual wetted wing area. So the user can go back here. Once again, sort of count the squares. Okay, so the reference wing area is here, illustrated by that line. Now we can go in and calculate how much this area is compared to this reference area, and then input that back into here, and that will determine this S hidden versus S exposed, and then you can plug it into this formula here, and that will give us the wetted area of the wing. So now that we have that, we can determine things like the parasitic drag as well as our lift curve slope and our lift induced drag. So we'll look at lift curve slope first. I have this function here, and this is basically just going to give us the CL alpha as a function of Mach number. So basically, as you go through the regimes, what is the lift curve slope that you're looking at? As you go up through the transonic regime, it's going to spike, and then as you go supersonic, it's going to decrease. So this will be good to allow us to see what is the maximum CL that we can get, knowing our stall limits, basically, of the airfoil. And then that is just a couple of empirical formulas, mostly from Raymer, where it comes in and determines it based on, for the subsonic, as a function of things like your aspect ratio, your beta value, which goes steps through Mach numbers. And then for the supersonic, you're going to have to input this from the charts, the traditional charts found in Raymer, and I can show those later. But they are pretty easy to use, so that it'll prompt the user where to go get them, and then they can enter those values in as a matrix. And it will calculate the subsonic regime, the supersonic regime, and then interpolate between to find the transonic regime. We'll end up plotting that. I think that's the first plot. In total, this tool will have about 41 plots, so a lot of information that's outputted, but it will also then take the subsonic and supersonic CL alpha values and output them if you want to look at them numerically rather than graphically. Okay, so now that we have the lift curve slope, we can get the parasitic drag buildup taken care of. So we'll go to the aero component drag buildup. This is one of the more intensive functions that has a lot of different values that are inputted into it. So we can go here and take a look at sort of what's going on in this function. So the first thing that we're going to do is take a look at basically a sanity check value. So we can do that using the equivalent skin friction method, where all we really look at is the wetted area as well as the skin friction coefficient for a standard US Air Force fighter jet. And that will give us a value that we can use to later compare and see whether or not what we have is reasonable, or if it's too high or too low. Okay, so we're going to start off by looking at the different component buildups in the subsonic regime, and we can start with the wings. So the first thing that we are going to calculate is our cutoff Reynolds number, which will allow us to determine the percentage of the wing that is either laminar or turbulent, as well as factor in the roughness of the skin, which comes in this K factor. For this, it's going to be estimated that the entirety of the body is turbulent, not only to allow for a more conservative approach, but also to account for the fact that military aircraft paint is quite rough, and it will probably trip the flow earlier. So you're not going to see a large percentage of the wing, and certainly not the fuselage. That would be a laminar flow. So this will calculate the cutoff Reynolds number based off of that skin friction roughness, which will then be used to calculate the coefficient of friction based on a function of the Reynolds number as well as the Mach number. This form factor is used to calculate viscous pressure drag due to separation, and then this Q factor is the interference factor, so like the intersection between the wing and the body, or the intersection between the tails and the body. From that, we can calculate the CD naught of the wing by calculating it based on this formula here, where we just multiply all the values together and then multiply by the wetted area of the wing to get that. So moving forward for the tails, we do something very similar. I think we do, yeah, looking through this, almost everything follows a very similar form, where it's going to be the CD naught of that component is equivalent to that skin friction factor times our form factor times the interference factor times, and the reference area is always the wetted area of that component that we're looking at. And then this component will be as a function of the wetted, or of the reference area of the wing. So that's the standard reference area that we use to non-dimensionalize drag, and we'll stick with that for this. Moving forward, let's see, the fuselage and the boundary layer diverter are all the same as the tail and the wings, so we can skip past those and go to the total component drag. So this is going to be the sum of all of these, and then there's the reference area, like I had mentioned before, that it's non-dimensionalized over. We can also calculate miscellaneous drag, so that includes drag from our payload as well as drag from leakage and perturbance. So we can sum those two together along with our component drag and arrive at the total subsonic drag. So this is going to be different across different altitudes and Mach numbers, which is why it's iterated through in a double loop. Moving forward for the supersonic regime, we do something similar, but instead of having the form factor, so that FF function, which calculates the pressure drag due to separation, what we will end up calculating is the wave drag, which is going to be the drag due to the pressure differences across oblique and normal shocks in the flow. That's a little bit harder to estimate, I think. Let's see. So these are all standard, Reynolds number, form function, and then the wetted area. So once we get to the wave drag is where we can see some interesting formulas where we calculate the wave drag as a dq value, so that's non-dimensionalized over the dynamic pressure, and then by dividing by our reference area we can back out the parasitic drag coefficient. But we can see that as it's a function of both the fuselage length and the maximum cross-sectional area squared. So those are two important factors that we can use later on in the design process to see, for instance, iteration 1 of this unmanned vehicle will have too much wave drag, and it will not allow it to reach its maximum Mach number per the requirements. So we can come back to this equation here and kind of see what are the different things that we can change in this formula by obviously changing the design to reduce that wave drag at supersonic speeds. We also account for leakage and perturbance drag, about 12%, and then we are going to sum all those together, and then that will arrive at the supersonic drag. Once again, that's going to be iterated in a double loop to allow for variations in height and Mach number. So for the transonic regime, we need to know the drag divergence Mach number. We can get that using the Boeing estimate. That's a figure in Raymer that I point the user to. They can input that in, and that's inputted as the Mach drag divergence reference number. And then from there, what we can do is calculate our CL value, and then go and use another figure in Raymer that will allow us to put in some different values here, and then we will calculate the drag at 4 different points. So that's going to be at Mach 1, at Mach 1.05, at the drag divergence Mach number, and at the critical Mach number. So the critical Mach number and the Mach drag divergence number are going to be estimated based on that Boeing drag divergence number, as well as the design CL, and that will be for this value, and then which is the drag divergence, and then the critical Mach number will be that drag divergence minus a little bit, so about 0.08. That will put us at our critical Mach number, and you can see those two values in here. So this is going to be our total drag buildup. These are the X values, so our Mach number that we're going to be plotting on the X-axis. So As you can see, we started it with 0.2, goes all the way up to 1.8. Like I said, we have 1.05, 1, and then the critical and drag divergence in the transonic regime. So this column, this column, this column, these 5 right here, that's all transonic. Anything before that, that's going to be our subsonic regime, and then we have our supersonic. And then we can take those, transpose those matrices, and add them all into one large matrix, which we will just call CD naught. And then that, along with all of the X values, are going to be outputted, as you can see. So we'll have the supersonic, the subsonic, the combined with transonic, and then all of the X values. These will be outputted back to the master file where then they can be plotted. So this is the first time that we're going to use our modified Acoma interpolation method. So this allows for a nice smooth interpolation. We have discrete points, and especially in the transonic regime, you're going to need to interpolate to have any sort of function that will be valid, anything that is actually usable. This basically will do, I believe it's a second order method for the interpolation. Not entirely sure, but I know it's a good method, and MATLAB has a built-in file where you can specify the discrete number of points, in this case between the beginning and the ending Mach numbers, and we said 0.001 to allow for a lot of different fine points, so we can pick any single one when we want to do calculations. And then we will end up plotting that, and you'll see that plot in a little bit when we actually do the example. That's plot number 2. So moving on, we have our leading edge suction factor. So this is going to be used to help calculate our K factor in a little bit, which is our obviously drag due to lift factor, which comes into play later on, as you can see, right? Our lift to drag ratio and drag polar will come in K. Drag due to lift will be here. So the leading edge suction factor is how well the airfoil sucks air back from the leading edge downwards due to adverse pressure. It's dependent upon your CL range as well as your designed Mach number. So we can calculate here, based our cruise height, and then our design CL based on our cruise Mach number, cruise height, and then half of our fuel burned. So that will print out the design CL, and then we have to go into Raymer once again and put in some values for the leading edge suction factor. And then that will plot that, and you can use that to later specify the K factor, and which we will jump into now. So the drag due to lift is fairly simple. It's going to be an averaged value between K0 and K100. So K0 is going to be the inverse of your lift curve slope, 0% suction. That's going to be your worst case scenario. And then K100 is going to be the inverse of pi times your aspect ratio, which is 100% suction, and that's going to be best case scenario. So realistically, depending on your CL value, you're going to have somewhere in between. So what we can do is take an average, not an average, but a calculation between a weighted average between the two, and plug it in as we go through different CL values as well as different altitudes and Mach numbers. So that will calculate that in both the subsonic and then later on in the supersonic regime, where the lines collapse and just become the inverse of our lift curve slope. So then we can put those two values together and have an overall K range between Mach 0 and Mach 1.8, which will then be outputted as just K back to our master file. So once we get our K factor, once again, we can plot that, and I'll show that as we do the example, but it will show different lines at different Mach numbers as well as different altitudes, and they start out separate in the subsonic regime, and like I said, they converge to and collapse on a singular line as they go through the supersonic regime. So now that we have the K value as well as the parasitic drag buildup, we can calculate our lift to drag ratios, and that will be very big in determining the performance of the aircraft later on. So we can hop over to the lift to drag function now. So this is going to be, once again, calculated at a range of different altitudes. So for the different Mach numbers, what we will end up having to do is do a quick calculation for, obviously CD is your CD naught plus KCL squared. We will do that across a different range of CLs, so not just the design CL, but the potential CLs ranging from about 0 to, I believe, about 1 or 1.2, depending on which values I used for this particular one. I don't recall, but it will go across the range of CL values and then calculate your CD naught. And at the end of that, we can then plot that, obviously, CL versus CD, and it will do your standard parabolic shape. And then also we can do L over D as a function of Mach number. So for the plot where it's L versus D, we'll have multiple lines, and each line will correspond to a different Mach number. And then we'll have multiple plots dictating different altitudes. And then for the L over D as a function of Mach number, we'll simply have multiple lines for different altitudes, but not different lines for Mach. And we'll see that later on when we calculate the example, and it'll spit out a lot of different plots. So we can step out of here and go back to our master file. So that's the end of the aerodynamics section. It calculates the majority of the things that you need, such as your maximum lift to drag ratio, your drag due to lift, your parasitic drag, your overall drag, which will be very useful later on when we're doing our performance calculations. So the next thing that we're going to look at is the propulsion system. So we can go into this pressure recovery function, which will create a plot that shows the pressure recovery of different inlets compared to your mil standard. So MILI 5008B, which is the pressure recovery that engines are going to be designed to. So whatever tabulated values we have, we need to adjust compared to that. And we can do that by first calculating the actual pressure recovery depending on the inlet type, and then using a formula to find the difference in, down here we have the thrust loss due to the difference in the actual pressure versus our reference pressure that the engine is quote designed to. So looking for the function of our reference engine. Let's see here. I think we can just go and look at it, but it's called in that function, and this reference engine is basically going to be a tabulated value from the F119 engine, the Pratt & Whitney, and you can find this in the appendix in Nikolai. So as you can see in the comments here, we have basically all of the tabulated values of the thrust and the specific fuel consumption as a function of throttle setting, altitude, and Mach number. So that's going to be very useful. We're basically going to take this, scale it for the size, and also do all of the installation effects, as well as the advanced technology factor, because this engine is about 25-30 years old. So in the future, we will have hopefully something that will be a little more fuel efficient, and we account for that using that. So back to the pressure recovery, we have a variable switch basically for the type of inlet duct. So if we have curved or straight, you're going to have slightly less loss in a straight duct than you would in a curved duct. And then also for the actual inlet, we're going to assume full recovery minus this value for subsonic, and then supersonic, you're going to be traveling across a normal shock wave for a pitot inlet, and then you're going to be going across a series of oblique shocks for an external compression ramp. And I did not do a mixed compression inlet due to the relatively low maximum design Mach number for this aircraft. So those external compression inlets are often seen on Mach 2.5 plus aircraft, which we won't be reaching those speeds. So I had the option between a normal shock inlet and an external compression variable geometry ramp inlet. So once we put in those values, it will calculate it based on, and this one I did, I designed the inlet, which I will show in the report, and it has a series of 2 oblique shocks that it travels through, and it's going to be variable geometry for maximum pressure recovery. So once it calculates that, it will then plot it so you can visually see and make sure that it is, a reasonable value. And then you can calculate how much thrust will be lost, and it will adjust the reference thrust from the engine to account for that pressure recovery on the inlet. And then it will output the reference and then the actual pressures as well as a thrust adjuster value back to the master file here. And then we can account for other installation effects. So things like drag due to, the nozzle and boundary layer bleed in the engine face, as well as excess air going over the cowl, having cowl drag, those sort of factors. So we can go into the install function now and take a look at what sort of things we account for. So the first thing that I did in this was create dynamic pressure tables, because a lot of these are functions of the different dynamic pressures. These are all at different altitudes. So for instance, Q10K is 10,000 feet. We have sea level all the way up to 60,000 feet. So for the nozzle drag, it's going to be a function of the type of nozzle, the maximum area of the fuselage, and then of course it's going to be dependent on what altitude that you're going to be at. So that's where the dynamic pressure comes into play to account for that. And then early on in the initial parameters of the master file, you can see a nozzle drag toggle, and this will allow you to choose. If we go back there now, we can see what each type of those is. So we have things such as your convergent iris, ejector, 2D nozzles, variable ejectors. Those are all used not only for calculating the drag, but later on, I believe some of them will be used for calculating the weight. For instance, the 2D nozzle, if it's a vectored nozzle, will have additional weight. So that will be a factor that helps determine the weight of that. We can go back to the install effects now. So we have our nozzle drag, and then we also have our inlet drag. So the inlet drag is going to account for a combination of multiple types of drag that are sort of lumped together. This is very hard to estimate, especially at this point in the design process. So it's a little rougher than some more refined areas that you might see in other sections of the code. It comes from Raymer on page 491 if you're interested in looking, and it goes through and calculates once again at between sea level and 60,000 feet, and then adds those on to the installed thrust values, or sorry, the uninstalled thrust values to become the installed thrust values of the reference engine, which you can see here. So these are going to be all the installed thrust based on the reference engine, the inlet drag, the nozzle drag, and the pressure recovery, and the reduction in thrust due to that. So once we have all these, now we have not only the thrust, but also the specific fuel consumption across Mach numbers, altitudes, and throttle settings for a realistic engine, which is very exciting. So coming back to the master file, we'll go back to where we were in the code, which is right here. So I initially planned to do some structures. I wasn't able to get the VN diagram done, so that's what that section is. And then we can move on to the weight section. So this is going to be your component weight buildup. These use the equations from chapter 15 in Nikolai for the USAF fighter jet. It's going to account for basically everything on the aircraft that is part of the empty weight. And then later on, we can add in the payload, and then we will take our maximum gross weight, subtract those two values to determine the new fuel weight. Obviously, we can't just use the exact same weight, because then, this is based on the maximum gross takeoff weight. They're all functions of that. So we'll need to iterate through to actually converge on the proper weight when we do the component buildup, but this will give us a good estimate. So for the structures, propulsion, and all of these other values, I have separate files for each one where they are called, just to save some room in this master file. But they're all fairly similar, where you basically take in different parameters that are, specified by Nikolai. For instance, in the wing weight, you're going to take in, common things such as your aspect ratio, your taper ratio, the area of the wing, the sweep of the wing, how thick is your airfoil, all very important things. in determining that from those equations. It'll take it in, it'll calculate it, and it'll bring back two values: the weight of the wing and then the nominal weight of the wing. So the weight of the wing is with your composite adjustment. The nominal weight of the wing is if you were to do a standard, like aluminum or titanium design, and then later on we can compare the two, find a difference, and then use that to later adjust the composite adjustment function that you saw in the initial weight estimation function. So I'll jump into one of these and kind of show a couple of the nuances, but we don't need to go through all of them. That will take a long time and not really add much. So we'll hop over to the wing weight. So like I said, we bring in all these parameters. We have our ultimate load factor of 13.5, so that's 9 times 1.5, and then we calculate using this very complicated equation that was derived somehow. I'm not entirely sure, but like I said, I believe these are the weight estimating relations from Nikolai. So it'll come in and it'll calculate the weight of the wing. So then the first two things that we're going to do is adjust for composites. There's different estimates in the same chapter of Nikolai for different components, so they're not all going to be 0.8. For instance, the air induction system might be 0.9 and the fuselage might be 0.85. But nonetheless, this will adjust it to account for the reduction in weight from composites. And then we will tack on the margin of 1.06, which is what's used at Lockheed Skunk Works. So I thought that would be a good value to use. That just allows for future weight creep in the design process. Multiply the weight of the wing by the composite adjustment as well as the margin, and then that is your new weight of the wing, which is then outputted along with the nominal value, which is the same calculation minus the composite adjustment. You see it's not multiplied there. And that is done for all of these. One other one of note, I think, is the tail weight, because that has obviously, to choose between a standard and a V-tail, which is going to result in a different weight. So the weight of the V-tail actually came from Gunlock in his designing unmanned systems. I couldn't find any other equations for it, so that came in through there. And it's basically a function of the weight of the tail vertically and horizontally times a function of the dihedral angle, the cosine and sine squared of that. And then we have, obviously, if we want to do a standard tail, then it's just the normal equations from Nikolai, which can be used to calculate the weight of each one individually and then added together for the total empennage weight of the aircraft. The last function here in the weight section that I want to show is the avionics weight. So the avionics weight is a little different. It's hard to estimate avionics using an empirical formula, so you need to sum up what you estimate the aircraft will utilize. So these are all of the avionics that are going to be included for both the manned and unmanned. Obviously, when you have an unmanned aircraft, you're going to have to account for things such as integrated sensors in the skin, or perhaps external sensors, command and control data links, and any sort of payload data links that are going to be not seen on a manned aircraft. So that's going to add some weight. That was very hard to estimate. I ended up at about 250 pounds. For a manned aircraft, obviously, there's going to be things in it that, for avionics, that an unmanned doesn't have. For instance, your heads-up display and your intercoms and, let's see, lead computing optical sites. So all of these are only found in the manned aircraft, but nonetheless, they're added in. So these are all of the values that are found once again, from Nikolai. I believe in chapter 9, there's tabulated avionics weights as well as densities to find the needed volume for them. So we can go back to the master file now. So we've covered the entirety of the weights. Now we can talk about the performance of the aircraft.
Okay, so for the performance of the aircraft, we're doing the standard stuff like our power required curves, the thrust required curves. We're going to be looking at the instantaneous turn rate, because that was one of our key mission requirements. We needed 25 degrees per second, and the corner speed was also specified as anything greater than 345 knots. And then we can also look at the contour plots of specific excess power across different load factors, so we can see sort of how much excess power we have for things like acceleration and climbing, which will be really important for this aircraft during combat. So the first thing we can look at is our power required curve. Now, traditionally the power required curves are for piston-driven engines or propellers, so this one isn't as useful as the thrust required curve for the jet engine, but I created it anyway just so we have some extra plots to look at. So we can go over to the power required curve, and also they're very similar. It's just multiplying by velocity, so the code itself is quite similar. It's very easy to quickly copy and paste and change it over, so not much added work for a lot of added functionality. So it's broken up into the power required at different altitudes. I think it goes between sea level and 50,000 feet, which it does. So we're bringing in some of our main aerodynamic parameters as well as the engine performance, which is why it was very important to calculate that earlier on, so we can actually analyze how well the aircraft meets its mission requirements, which is through these performance metrics. So what we're going to do with this is first we determine what CD0 and K values of the main arrays are needed for at sea level, right? Because this is going to be a large matrix that contains all the CD and all the K values, so we need to divide those up, and then we need to do the same for dividing up the installed thrust into installed thrust instances that occur at the proper velocity. So we can do that here and then convert that to power available by simply multiplying by that same velocity. And then we can find the power required using thrust is equal to drag and expand drag into the lift due to drag as well as the parasitic drag. So that's seen there. And then we can plot that. And we'll have three lines. One will be the power required, and then we have the the power available. In this case, thrust available will be the other function, but the power available when the engine is at 100% throttle and afterburner, so that's defined as wet, and then 100% throttle but dry, so no afterburner. And that's important because one of our requirements is the ability to supercruise, so that is defined as dry power only, no afterburner. So in order to assess that requirement, we're going to need to look at what's our maximum velocity at different altitudes when we're using simply the dry setting, and then also the wet setting will be used to determine, like for instance, how much power is available when we're going, at the maximum afterburner for a dash into combat or for combat itself. So this is repeated, the same calculations basically for a bunch of different altitudes in increments of 10,000 feet. Nothing really much changes, just that we're referencing different parts of the arrays for instance, the CD0 values or the K values, as well as different thrust values. And then those are all plotted on separate plots and labeled as such, so when we look at them, we know what we're looking at. So we can now hop over to the thrust required curve, we'll go back to the power required curve because we want to look at also what's outputted from it. So it will be the power required at all those different altitudes, and then that will go back into our master file here, and we will be able to see that it will be added to our workspace here. Once we run this, we'll then be able to quickly reference, if we wanted to do a trade study, we could quickly say, okay, what happens if we change the power required, then rerun an individual subfunction and recalculate it. So going now to the thrust required curve, this is very similar to the power required. Like I previously stated, the only difference is now this thrust required here is going to be divided by velocity, and these thrust availables are not going to be multiplied by velocity. So it's very similar in terms of we're still breaking up CD0 and K into the specific parts of the arrays that correspond to what we need. We're still plotting it with three lines where we have thrust available in the dry setting and thrust available in the full afterburner. And then thrust required will be that sort of parabolic distribution, and then we can see where the lines intersect, trace it back down, and determine the maximum velocity that we're able to achieve. So this is repeated for sea level all the way up to 50,000 feet again, each one corresponding to a different figure. So going back to the main master file now, we can see that's those two sections there. So now we can talk a little bit about the instantaneous turn rate. So the instantaneous turn rate, you're going to have an intersection of the stall limit as well as the structural limit. That's normally at a load factor of about 9. And the intersection of those two lines will be defined as the corner speed, and then we can also trace that up to the y part of the graph, and the y value will be your turn rate. So we can go and look at the code for that now, instantaneous turn. So this is going to be done at the combat weight, and combat weight is defined as half of the fuel burn but still have payload. So we can define the stall limit by simply using the equation for the stall velocity, iterating through that, and then calculating basically, across different n values what is our different stall value, right? Because it's going to be dependent on the load factor of how much lift you actually need. So that will change the V stall value, because this weight combat is then multiplied by your load factor. So it's not just lift is weight, but lift is n times weight. And then from there we can calculate the phi dot stall, which, like I said, will be plotted on the y-axis of the graph, and we'll see that when we do the example. Then we have the structural limit, which is going across different velocities, but setting n as a constant value equal to 9, because we know that's our ultimate load limit from the requirements. And then that's going to be plotted 2 times, one of which the x-axis is going to be in knots, and then another time where it's just going to be in Mach. So that's 2 separate plots, but we just have different x-axis, so we can see, and we don't have to convert between knots and Mach. We just have 2 plots that will give us exactly what we need. And this was done at 20,000 feet. Once again, from our requirements database, they specify that we need to know the requirement specifies that the instantaneous turn happens at the 20,000 feet. I also went ahead and calculated at 30,000 feet, just so we had some extra information about the aircraft, and I repeated the same process. The only thing that really changed was that the atmosphere function will obviously be returning the densities and speeds of sound at 3,000 feet, and that will create 2 new plots, once again, one with knots on the x-axis and one with Mach on the x-axis. So there's no outputs from this function. It's simply an input, and then it creates the plots internal to the function. So nothing to really see in terms of outputs. So we'll go back to the master file, and then our last external function is our excess power. So the excess power is going to be the difference between thrust and drag at any Mach number and load factor, which will allow us to determine, once again, how much we have to, say, accelerate or climb. And you can see all of the inputs there. This is going to be done at 30,000 feet because the requirement database specifies PS 0 at, I believe it's Mach 0.9 and at 1.2 at 30,000 feet. So we will have to go and analyze it there. Obviously, we could expand the code a little bit and put in different thrust values, and we would be able to determine those contour plots across all of the altitude regimes if we wanted to. So we can go to excess power now, and you see, so we can define a vector of the load factors that we're interested in. I did 1, 3, 5, and 7. At 9, it's not going to be very much excess power. We'll probably have negative excess power, so it won't be as indicative, but if we wanted to, we could add 9 in and just simply expand it. That's going to be across a range of both subsonic and supersonic Mach numbers, so across the whole regime. Once again, we're going to be determining the K factor, the CD naught, and the CL values that we need from our large array, so that's what these lines of code are, and we're going to be determining the combat weight in the same method that we did when we were looking at the power and thrust required, so half fuel burn. And then we have an interpolation function for the K to interpolate at different CL values. Maybe our values are not discrete, so we have to figure out what's in between. So we use a linear interpolation for that. And then what we can do is do a double for loop. So this will iterate through the I column, or row, sorry, corresponds to the different load factor, and then the J column corresponds to the different Mach number. So this will go through, and for one load factor, it'll calculate the excess power across a bunch of different Mach numbers, and then it'll iterate through again for all the different load factors. Then we can divide those out by columns. So we'll take row 1, all the columns, and then down through row 4, and then each of those row vectors will correspond to a constant line of load factor as you go through the regimes of Mach numbers. Once again, we're going to use the modified Ackermann interpolation method in the plot of this. There's a bit of a gap between subsonic and supersonic in the transonic regime, so we need that interpolation to allow for a smoother line, better visuals on the plot. So that's what that's for, and then you can see we're going to create a figure, plot that in. We have a constant line at 0, so it's very easy to see, and then obviously a legend sort of dictating what's going on. This is at 30,000 feet. We could repeat this, like I said, for any altitude, but for the requirements, we're only looking at 30,000 feet. So we can go back now to the master file, and that is the end of the performance section. So the very last section is going to be the cost of the aircraft, which is arguably one of the most important metrics, as if you design something great, but it's far above the LCC of the F-16, then obviously the Air Force most likely would not be interested in purchasing that. So we wanted to make sure that whatever we calculated here as it comes through meets that cost requirement, which was specified in the mission requirements. So using I believe it's the RAND equations. They were from Nikolai as well, but so chapter 25 in Nikolai, you can go and take a look, but they are mostly a function of the empty weight of the aircraft, the maximum velocity, and then how many you're going to produce, so like the economy of scale there. And then you also need the inlet turbine temperature in order to determine how much the engine is going to cost in development. So the maximum velocity, you can put that in from your thrust required and power required curves, and that's going to be an input in knots. The empty weight, that's already known. It calculates that using the empty component weight buildup. And then the one variable that's really you need to kind of think about is the production aircraft produced. So I went ahead and put 800 because doing some research, I found that there's around 1,000 active F-16 aircraft in the U.S. Air Force arsenal. Of about 750 are the F-16C variant, which is the single-seater. So that's the aircraft that we'd be aiming to replace. Obviously, you're going to produce a little bit more than just the 750 because you'll probably need a two-seat trainer variant. So I went ahead and put 800 to account for spares as well as trainers. And then I did 8 for the number of development aircraft produced. Once again, this is very hard to find any historical data for, but 8 seems like a decent number to build to bring through flight test, and these can eventually be retired or integrated back into the fleet if there's enough or if there's minimal changes that need to be made. So then the next thing that we have are some inflation values. These are using the consumer price index. A lot of the equations from Nikolai were in 1998 dollars, and then there was a couple that were in 2002 and 2003 dollars. I think those might have been from Raymer and Gunlock. So these are just values that will convert these to 2021 dollars, which is what all of the calculations for this will be based on. And then the avionics cost is estimated from Raymer as a per pound cost of avionics in 2021 dollars. A little hard to find, but estimation for the avionics without knowing the exact price of every individual component from a market vendor is needed. So then what we can do is look at the hourly rates, because some of these equations will not yield the actual cost, but rather the number of hours, which then need to be multiplied by the rates for those hours to determine the actual cost. So these are equations that were developed from page 633 in Nikolai, where the input is the year, so we can just put in 2021, and this will give us the hourly rates of tooling, engineering, quality control, and manufacturing in 2021 dollars. So then what we can do is we need to figure out what our research, development, test, and evaluation costs are going to be, so we can amortize that across a number of certain aircraft and then add it to the individual cost of manufacturing to achieve like a per unit cost of these aircraft, as well as the total LCC once we add in the operation and maintenance costs. So these equations are all either going to give you the hours or the actual numbers. You can see it varies, and they're almost all functions of just the empty weight, the maximum velocity, and then the number of development aircraft QD, which was 8. And then you can calculate the cost of the engine, and then multiply that by the number of engines that would be needed. So for research and development, that's going to be more than one per aircraft, because you're going to want to have extra spare engines in case something were to go wrong. So if we go down here into this, we can see that we assume 2 engines per test aircraft for a total of 16 engines. So there's that factor of 2 here with the engine costs. So we're getting ahead of ourselves. We'll go back a little bit. For an unmanned aircraft, we need to account for the fact that there's going to be ground control stations that might not necessarily already exist. So we might not be able to use pre-existing infrastructure. We should take that into account when we're determining the cost of that system. So we know that for an aircraft like this, it'll most likely be an immobile ground station. So we can calculate that by setting FHAN equal to 1, mobility to 1, and then estimate the typical range between the UAV and the ground control station as the outer radius of our combat range, which is about 305 nautical miles or 350 miles. When we plug that in here, we can then get the the amount for the ground station in $2,003, which we will then later convert using one of our inflation adjusters. And then the next thing that we need to estimate is the cost of the software. So back in the day, maybe in when they were developing the F-15, there was probably around 250,000 lines of code in that aircraft. But if you look today, where we're talking about the F-22 and the F-35, these can easily be in the millions of lines of code. So obviously, it's not going to be a fully integrated stealth fighter, so we can ease that back in terms of the number of lines, especially if it's a manned aircraft. However, if it's an unmanned aircraft where you're going to be dealing with potentially some flexible autonomy in that design, you're going to be in the millions of lines of code. I estimated it as a 1.5 million lines versus 500,000 for the manned version. So these are the going to be plugged into the Kokomo equations, which is a constructive model that I got from Paul Bevilacqua in one of his recent cost reports that he presented in spring of 2021 to the 451 class. So from there, we can estimate the number of software hours needed based on the number of software lines and the complexity. We put this as the most complex because it's going to be, an advanced aircraft, and it won't come easy. So it's better to estimate as a more conservative approach as harder than average. So that will be a 700 factor here. We put in the software lines in thousands, or hundreds of thousands, so divide by 1,000, and then we have our factor. So the software rate is the hourly rate that was estimated using a reference that will be shown in the report, and then from there we can get the total software cost to develop this. So from there, we can put that all together and we get the total research, development, test, and evaluation cost. And the next thing that we need to then calculate is going to be our total production cost. So how much does it cost to build all of these aircraft and get them into production? That's going to be estimated using similar equations, but instead of just looking at the development aircraft, we need to look at production and development minus the development aircraft. So that's these parts of the equation right here. And then we also need to account for the fact that we're going to have individual engines for each aircraft, and then when we add all that together and adjust for inflation, we can get our production cost here. So for the unit cost, we now can take the production cost and the RDT&E cost, amortize the RDT&E over a certain number of units, add that to the production cost by per production unit, and then that will give us our unit cost. So we chose to amortize it over 300 units just because I wanted to allow for that to be recouped fairly quickly, and then over the final 500 is when you'd be making a larger profit as a manufacturer. So then the final part of cost estimation and the life cycle cost is going to be your operations and maintenance. So that will vary drastically between manned and unmanned due to the fact that with an unmanned aircraft, you have the ability to not fly during peacetime. You don't need to train a computer. You don't need to let it practice so it retains its effectiveness in combat as you would a manned aircraft, right? People flying, they're going to need to continually practice, and that adds to a lot of peacetime flying, and that increases the operational cost of this system. So to account for that, Nikolai has an excellent section on page 648 of his book that details a very good cost breakdown between a squadron of 24 F-16 see aircraft versus a squadron of 24 unmanned combat aircraft that would be similar in nature to a lightweight fighter that I'm designing here. So I was able to take that and plug that in, and to account for the fact that we're dealing with an advanced technology factor, we can reduce that fuel cost by about 20% to account for that reduction in fuel burn, while keeping things like spares and munitions and the maintenance constant, as those are not going to change regardless of the advancements of the capabilities of an aircraft. You're still going to need the same support and training and personnel for those. So by doing that, we can calculate the yearly cost by 24 aircraft, and then multiply that by the number of actual aircraft to determine, how much it would cost to operate the entire fleet. So for ours, it would be 800 aircraft versus the F-16, it would be about 750. So that would give the operation and maintenance costs yearly, and then we have to assume a time period over which we assume that both of these aircraft are operational. So doing some external research, there's a very strong inclination that the F-16 has the ability to fly for another 25 years. So I went with that and said, okay, if the F-16 were to fly for 25 years based on the costs laid out by Nikolai, how much would it accrue over the remainder of its lifetime? So just operation and maintenance, because obviously, those systems have already been acquired, and there will be some sustainability in there, but I don't have enough information about that to make any assumptions. So we're looking at just the operations and maintenance of the F-16 versus the entirety of the LCC of this new novel aircraft. So by doing that comparison, we can first calculate the LCC of this aircraft by simply summing the three sections together, and then for the remaining F-16, we can find its operating costs on a per year basis per 24 aircraft, take the entire fleet, divide that by the 24, then multiply by the entire time that will be operating. So that will give us the cost of operating the entirety of the fleet for a remainder of the 25 years. I think that came to around $60 billion, which we can look at when we do the example. In comparison to the unmanned variant, the life cycle cost was around 35 million, and that is due to the large reduction in operations and maintenance costs. So looking at that, you can see that if you were to have a manned aircraft, that would have to account for the cost of production and development. It might not necessarily be more cost effective, even if it has increased capabilities over the F-16, but it might be possible to design an unmanned variant that you can reduce the operational and maintenance costs, and you have increased performance and capabilities, as well as a reduction in the overall cost. Okay, so that's the entirety of the code. We can now go through the example like I talked about. We can run the script pretty easily. All we have to do is click run up here like a standard MATLAB script, and then it will prompt us in the command window for our first user input. So we can see here that it calculated the initial weight for both the air-to-air and the air-to-ground mission. Now we see that by comparing the empty weight and the gross weight of the two, that they are not matched up. Like this is going to be about 2,000 pounds lighter than what we would need for the air-to-ground mission. So that's telling us that we can incorporate additional payload into this air-to-air mission while still meeting all of our mission requirements. Since it's needed to be this heavy for the air-to-ground, we can get away by adding more payload to the air-to-air than is specified by the requirements. So we can go ahead, and I already did all these calculations that you're going to see being put in, but I did the calculation that if we put in 1,800 pounds of payload, which was removing some of the bullets from the 20mm cannon and adding in 2 additional AIM-120 missiles, that we should be able to, we don't put that there. We first have to specify that it's not satisfactory, and then we can put that in. 1,800 pounds for the air-to-air configuration, and then the 4,000 pounds, which was required by the specifications. That's 2 GBU-27s. And it will recalculate the initial weight estimation as now 20,400 roughly for the air-to-air and 20,000 about 380. So we can see that those are quite close, as well as the empty weight of the aircraft. So the fuel weight's going to be different because this mission is going to have a larger payload, but it's going to be less fuel intensive, where this one is going to be more fuel intensive due to the maneuvers of combat and the acceleration, but we have a lighter payload. So what we need to do when we're designing the the internal volume of the aircraft is to make sure that we have the maximum fuel, which will be this. So when the aircraft is performing an air-to-ground mission, the empty weight is the same, but it will only be around 2/3 of the way full of fuel. So we can say that this result's satisfactory and move on to the next part of the code, which will be the takeoff parameter. So this is the first instance of referencing something out of Raymer. There's a couple figures that are too hard to code up, so rather than doing that, we just simply have a prompt to go to a certain page or certain figure in various books and pull out what you need. So the TOP is the takeoff parameter, which can once again be found in Raymer. On the y-axis, you're going to have the takeoff distance as a function of the feet. And on the x-axis, you're going to have that takeoff parameter, which is the value that we're looking for. So you'd go to this graph, you'd put in your 2,000 feet, which is specified by the requirements, go across to the ground rule, go down, and you'll see that takeoff parameter for this aircraft is 135. After putting that in, we can calculate the thrust to weight as well as the wing loading of the aircraft. Here it shows the wing loading needed to satisfy various requirements, you could say. For instance, cruise, sustained and instantaneous turn, as well as stall and takeoff and landing. So we look through and find our limiting factor, which in this case is going to be the instantaneous turn, requiring a wing loading of less than or equal to 47 pounds per square foot. So we know that we want a larger wing loading to have a more efficient cruise as well as more efficient loiter. However, we're limited by this, so in order to proceed, we're going to have to go with the limiting criteria of 47.56. We can put that in, and then it will calculate the thrust to weight ratio needed at takeoff to meet our requirements with that wing loading, which is going to be 0.81. So that's a little bit low for a fighter. That's okay. We can go back in a subsequent iteration and increase that thrust to weight. Obviously, anything above the thrust to weight of 0.81 will just result in excess thrust of the takeoff requirement, but it might be needed later on for performance, which we'll have to see after we evaluate this design. So for right now, we'll just go ahead and put in 0.81. So now we can enter the as drawn length of the fuselage. So I've already drawn up the diagrams, and I have them here with me, and I can look at these and say, okay, the estimated fuselage length was 37 feet, but after placing the wing and tail and determining the internal volume needed, it can be estimated that, it's not going to be 37 feet, but rather it will require 43 feet. So we can put that in, and then it's going to ask for certain parameters such as the maximum cross-sectional area, the wetted area on the top and side, and the diameter of the fuselage, or the maximum diameter, since it's not a purely cylindrical body. It's going to be tapered to allow for some area ruling. Once again, I've already calculated these ahead of time, so we can just go ahead and put them in. Nothing super exciting, just mostly counting squares on the grid paper and doing some calculations that way. So the top-down area of the fuselage is going to be 288 square feet. The side area is going to be 100 square feet. The maximum diameter of the fuselage will be 7 feet. Okay, so those are all the parameters needed for the fuselage, and then we move on to the inlet. So it'll tell us what our design Mach number is, which we had specified in these initial parameters here. And then from there, we can determine things like the capture area as well as the mass flow. So the capture area per mass flow for this design we can find once again in Raymer on page 303, and going to that we can see that it's going to be 0.0264, which we can put in, and then it will ask for another thing from Raymer, which is going to be the mass flow at that design Mach number and the design altitude, which once again we pulled from our initial parameters and the concept of operations. That is going to be 250. We can put that in. Now that that's done that, it has calculated what the inlet capture area is, as well as stated as what the diameter of the engine face is. So we can use these things to design the inlet the way we see fit. So for this particular design, we're dealing with a single inlet on the chin, and we're going to have the width be fairly similar to the engine face, so that when you go through the duct, you only have to change in one dimension rather than two. So you're going to be taking that flattened duct and expanding it into a circular duct, sort of similar to a diffuser, to help slow the flow from your high subsonic once you go through the normal inlet to around Mach 0.4 at the engine face, which is what's needed for proper performance. So we can go ahead and put that in as 3.15 feet for the width to match that engine face, and then that results in a height of around 1.16 feet. And like I said, we're dealing with a chin inlet, so the inlet's going to be on the fuselage. However, if it was elsewhere, we could specify that, and that would change some calculations later on. And then the top will be flat, and the bottom will be curved a little bit, so we will say 1 for one flat side. Now, a standard external compression ramp will most likely be 2 flat sides, something like the F-15, so that would be 1.33. But for this instance, we'll go with 1. And then from there, we can go back to our drawing where we've already placed the inlet and take a look and see from the inlet face, which is the beginning of the subsonic duct, or a little bit behind that would be a better estimation, to the face of the engine, how long is that duct? And that is going to be 19 feet. And then once again, we can go back to the drawing and look from the nose of the aircraft to the face of the duct and count the squares, see how long that's going to be, and it's going to be 13 feet. So now going back to the drawings, we can look at the top down and determine the area of the reference wing that's actually covered by the fuselage. This will be useful in determining, the area of the wetted wing relative to the reference area. So when we're doing the aerodynamic component drag buildup, that will be an important parameter. So that is 120 square feet of area covered. This part of the code is asking for values to help determine the CL alpha versus Mach in the supersonic regime. So the graph is divided into left and right hand sides. This specifies which side of the graph to use, L or R, and then these are the X values. We go up in the graph, find the Y values, and put them in as a matrix for each X value. So I've already done that, and we can put these values in. And the graph tapers off toward the end, so it's a constant value. Okay, so now we can enter in the Mach drag divergence number, which will be important in doing our parasitic drag buildup, because we need to know when we leave the subsonic regime and start increasing drag at our into the transonic regime. So that is going to be 0.855, and that's a function of our leading edge sweep as well as our aspect ratio. From there, it will tell us what our lift coefficient and the thickness chord of our airfoil is, and that will be used to help determine some values needed for the transonic regime. And we can put that in based on the figure shown in Raymer there, as well as the values that were outputted to the user. Okay, and one more. Okay, so now that we have that, we have to enter in the leading edge suction factor based on our design CL across our range of CL values. And that's going to be used to help find the induced drag due to lift. So we can go ahead and using, like I said, the design CL, we go to Raymer, we find the corresponding curve for a design CL of about 0.1, and we go along and read off certain values in the curve and add these in. And this will allow us to eliminate the need for using the Oswald span efficiency method, which is a little bit less accurate, especially in the supersonic regime. Okay, so the code is finishing up, and it has converged, and now it is printing out all of the figures. There's 41 in total. You won't be able to see them on this screen. I'll have to cut the video and go to where I have them saved. Unfortunately, the way I'm recording it doesn't allow you to show pop-up windows. But what I can do is show off a couple of the variables over here in the workspace. So after the code converges, there's a large list of all the different parameters that are basically very useful for the aircraft. So things like all of the individual empty weight components, all of the fuel consumptions and thrusts at different altitudes, all of the geometric characteristics of the wing and the tail, the weights, the costs of everything. So like I said, we can if we go in the code here, we can see that for the life cycle cost of the F-16, we can type in that variable there, LCC F16, and this will give us, that's around $66 billion. Now in comparison, we can just do LCC. Now this is going to be the life cycle cost of the vehicle that we are designing, and that's going to be around $34 million. So you can see it's quite the large savings due to that decrease in operational cost. If we wanted to look at unit costs, we could do that as well. If we wanted to see how much an individual aircraft would cost us, and $2021, it would be around 37 million. So if we wanted to, we could go and look up what the cost of the F-16 was when it rolled off the production line and adjust for inflation to see if this aircraft would be more or less expensive or around the same. And I'd done that previously, and I believe it was around 29 million. So this unmanned variant with the code in it and also the capabilities are going to be a little bit more expensive, but due to that reduction in operation and maintenance cost, we'll be able to actually save money in the long run. So this is some valuable insight. And now what we're going to do is switch over to all the graphs and we can talk through those. All right, so looking at the graphs, in total there's about 41 of them. They cover things ranging from the aerodynamics to the propulsion inlet recovery schedule to the performance. So we'll start off with the very first graph here, which is the lift curve slope as a function of your Mach number. You can see how it will rise up to the transonic regime. It spikes here, then it'll dip down dramatically as you go into the supersonic regime. One thing I'd like to note is that these blue squares are going to be the discrete points that the code actually calculated, and then this orange line here is going to be the modified Acoma interpolation method that I think I mentioned before that should allow you to kind of fare this line in here and give you a better representation of what is actually going on rather than just this discontinuous jump in the function, sort of in that regime where there aren't any tried and true method to calculate this value. And this will be valuable to look at what's the maximum CL value that is obtainable at any specific Mach number, because we know the limits of stall in the airfoil, sort of depending on which airfoil we have, what alpha is that going to stall at. From there, we can determine based on this graph what our CL is. And we know that we are looking for fairly aggressive CL. And this is also, sorry to note, it as a function of radians, not degrees. But, we're looking at around a CL max of around 1.5 in combat in order to have such a low wing loading while having such a high instantaneous turn rate. So we're going to need some sort of high lift devices most likely, because judging by this graph, it won't be applicable or won't be able to be reached. So moving forward, we have this great graph here which shows our parasitic drag coefficient CD0 as our function of Mach number, as well as across different altitudes between sea level and 50,000 feet. So as expected, it's fairly low in the subsonic regime, but then once you start to incorporate the transonic rise and wave drag, it becomes quite large. Ideally, we would want this section here to be around here, 0.035 or 0.04 if it was properly area ruled, or we had a reduction in the fuselage maximum diameter or an increase in the fuselage length, we could lower this. And we'll see later on that this aircraft has too much drag in the supersonic regime, so this is a very clear indication of having such a high CD0 that we're either going to need more thrust or to make the configuration of the aircraft a little slipperier so it can achieve that higher L over D as well as a reduced CD0. Moving forward, we have this simple graph, which is just our leading edge suction factor versus our lift coefficient. So this will be used to calculate K, but it was also plotted visually, so it can just be inspected to make sure that it's adequate. This graph really wasn't used much. It was mostly the numerical values that went into the graph that were used as a function in the code. So this is the drag due to lift factor that was previously discussed, your K value. So up here, this is where you're going to have K0 or 0% suction, the worst case scenario. And then down here is going to be your K100 or 100% suction and your best case scenario. So in between, we have a weighted average of these two values, and that depends on your leading edge suction factor, K. not K, but your leading edge suction factor from this graph, which serves as an input into this. And then once you reach the supersonic regime, they collapse as, I believe, 1 over CL alpha, or your lift curve slope. And then all the graphs collapse onto a singular value that continues to rise as this value up here continues to fall. Since this is the inverse of it, it will continue upwards as you increase in Mach number. So now the next couple graphs are going to be our drag polars, both in the subsonic and supersonic regime, as well as the L over D at sea level as a function of Mach number and then what CL value you're going to be at. So this is very valuable to look at and see in comparison of this L over D across different altitudes, CLs, and Mach numbers. We can determine what is the optimal Mach number and altitude to maximize loiter as well as maximize your range. So we know loiter occurs at max L over D for jet aircraft, and the maximum range occurs around 86.6% of that max L over D. So we can go through and find what CL we would need to be flying at, as well as a good Mach number and altitude. So we can go back quick because we skip past these, but this is just simply your standard CL versus CD, your drag polar, and these are all at sea level altitude. So there will be more plots that are going to be between 10 and 50,000 feet altitude, which we can look at in a second here. Nothing super important to note other than that you'd be able to, for any value of your CL, find a good value of CD. Moving forward, we're going to have very similar plots. These are going to be at 10,000 feet, so this is in the subsonic regime. The next graph is going to be the same plot, but in the supersonic regime. And then finally, we have the L over D across all of the Mach numbers at different CL values. So we can see that it's very similar to at sea level in terms of the max L over D attained. It's also going to be at the CL value of around 0.3. Moving forward, we have our drag polar at 20,000 feet in the subsonic regime. I won't spend much time on these to save on the size of this. I know this recording has already gone on for quite a while as we uncover the entirety of this code, but there's a lot to look at here. So we will simply pause on these for a second and then continue moving forward as we go through between 20,000 and 50,000 feet. I would like to note here at 20,000 feet, it seems that we have probably our max L over D that I have seen so far, indicating that for optimal loiter, it would be around Mach 0.65 at 20,000 feet. So now we've increased in altitude to 30,000 feet. This is the subsonic regime. Moving forward, we have the supersonic regime, and these lines are at various Mach numbers. Once again, we're going to look at the L over D at our 30,000 feet altitude. In comparison to the previous ones, you can see that we've dipped below 10 here, indicating that there's an overall downward shift, which we will see as we increase in altitude. Moving on, we have our drag polar at 40,000 feet in the subsonic regime, as well as in the supersonic regime. And then put all together, you can see that we have our L over D at 40,000 feet, once again below 10, indicating that in comparison to when we're flying at the lower altitudes, that there's been a shift downwards. So we're past the optimal altitude for loiter and maximum range. And then lastly, we have our drag polar at 50,000 feet in the subsonic regime, 50,000 feet in the supersonic regime, and our L over D at 50,000 feet. So moving forward, that's the end of the aerodynamic section. We can now talk a little bit about the propulsion. So this line here is the mil spec for what engines are designed to by the engine manufacturers for inlet pressure recovery. And then shown here is going to be our actual pressure recovery. So this is, as you can see, is for a pitot inlet or a normal inlet. So it will go across a normal shock in the face. And at the maximum Mach number, about 1.8, that's going to correspond to probably roughly 20% reduction in pressure, which can then be translated to an actual reduction in thrust, which is going to be more than 20%. So substantial losses, and it's worth looking at an external compression inlet, which has the option to be toggled in the code. So perhaps in future iterations, that would be something that would be explored just due to this very large difference in inlet pressure. And then here we have a graph that shows our percentage of uninstalled thrust utilized after our pressure inlet correction. So like I had mentioned, at a Mach 1.8, we're only going to be utilizing about 77 to 78% of the available thrust that's tabulated from our reference engine. So moving on, we're now going to talk about the power required as well as the thrust required. So here's a power required at sea level. The red line corresponds to full afterburner, and the blue line corresponds to max throttle setting of dry, so no afterburner at all. From this, we can see that our maximum velocity is only going to be around 1,000 feet per second, which at sea level corresponds to a little bit below Mach 1, so it's going to be around Mach 0.95. And we know that that's not going to be enough to meet the design criteria, especially later on when we look at the maximum Mach at 30,000 feet and 40,000 feet. So this is telling us that the aircraft is either underpowered or too draggy, or a combination of both, which is a reoccurring theme that we've seen as we go through and look at all of these different performance specs, as well as our aerodynamics and the propulsion model. So the remainder of these plots are just going to be the power required at 10,000 feet. These are all utilizing different tabulated values. So for instance, this line here is truncated early because there's no values beyond that. Now we could extrapolate that line linearly and see where that intersects, which seeing that it doesn't pass through any of the values, we don't necessarily know what our maximum speed would be at this at this altitude. So that might be something that we need to do in future updates of this code is extrapolate both of these lines outward. I think this is the only instance of this happening. The remainder of them should have enough values and the power available and thrust available to extend that line to where it intersects past on our power required and thrust required charts. So we'll move through the remainder of these fairly fast. They don't show anything super groundbreaking, except for the fact that we are once again underpowered, especially on the dry engine. We're only going to be reaching around Mach 0.9 at 20,000 feet, where our design goal, and at 30,000 feet, similar values, and our design goal is going to be around here. So in order to find a middle ground, we're probably going to have to reduce the power required as well as increase the power available, or thrust available. And here's the power required at 40,000 feet, and we can see from this that dry engine setting, we barely have enough power and to even maintain steady level flight. Now remember, this is all at steady level conditions, so any sort of climb or acceleration might not be possible at this altitude, just due to the lack of thrust available from the engine. And then once again at 50,000 feet, we see that finally on the dry setting, we do not have enough thrust to even maintain level flight, and that we would have to rely on afterburner if we were want to continue flight. These are very similar, except for the fact that we're going to be dealing with thrust required now. So straight lines here just indicate that whatever value was given was only given as a constant scalar and was not a function of the velocity. So that corresponds to two straight lines across the graph. Moving forward, we can see that once again these ones need to be extrapolated outwards, like the power required. These are very similar models, the thrust required versus the power required. Only difference is that the thrust required is not going to be multiplied by velocity, and our thrust required will not be multiplied by velocity, and nor will the thrust available. We'll move through these fairly quickly. This is just the thrust required at 20,000 feet. It will give us a similar velocity to what the power required showed. Same can be said about 30,000 feet. At 40,000 feet, we're approaching a lack of thrust available relative to what's required to maintain steady level flight. And at 50,000 feet, we can see that once again, we don't have enough thrust available in the dry engine setting, and that we would have to rely on afterburners if we were to fly at this altitude. So we've now reached our instantaneous turn rate at 20,000 feet. So this was what the altitude required specified in the requirements. So this blue line here is our stall limit. So anything to the left of this line is going to be in the stall regime. And then this orange line is going to correspond to the structural limit. So anything above it is going to correspond to a load factor larger than 9. So at the point of this intersection is the corner speed of the aircraft. And at this corner speed, we can go across and look at what our turn rate is going to be. So that's in degrees per second. So you can see at a corner speed of around 340 knots, we'll have around 25 degrees per second, which is meets the requirement. Now this was to be expected as the wing loading and thrust to weight dictated what this performance requirement would be. So we can say with safe bet early on in the process that this is one that can be easily met as long as we design the aircraft's wing to be large enough to accommodate that. And this plot is shown in knots on the x-axis, and then moving forward we have an identical plot. The only difference is we have Mach, so that way we can quickly look and see at what Mach number that occurs rather than having to convert from knots to Mach at that altitude. We also have similar plots at 30,000 feet. This wasn't required based on what requirements we had. I mean, we didn't need to do this, but it adds some additional information. We can kind of see, okay, what would the corner speed be at 30,000 feet? It might be advantageous to engage in combat at 30,000 feet then rather than 20,000 feet from an operational perspective, simply because now our corner speed is a lot higher. So we can get there from, if we're coming in an accelerated dash at supersonic speeds, we need to quickly decelerate to that corner speed so we can achieve our maximum turn rate. Now, that being said, the turn radius will not be as tight as at 20,000 feet, where it was 25 degrees per second. This corresponds more to around 22 degrees per second. So there's a bit of a trade-off. You get to the corner speed faster, but you have a reduced turn rate. So that would be something that would be a good trade-off from an operational perspective. And that same plot is shown here. The only difference is we have, in terms of Mach, which we can see now corresponds to almost Mach 0.7, where before it was Mach 0.55 at the 20,000 feet. This is the final plot, and this is the specific excess power shown at 30,000 feet. So these lines correspond to different load factors, and then on the x-axis we have at what Mach number they occur at. The y-axis shows our excess power, which is basically the difference between thrust and drag. The more excess power we have, the better or the quicker we can accelerate, and the better we can perform maneuvers. So the requirements specified that we have 0 excess power at a load factor of 5 at, I believe, Mach 0.6 and Mach 0.9, which we can see we do not meet. 0.6 we are actually at negative. So these graphs right here will need to be shifted up. And the way that we do that is either, once again, reducing the drag or increasing the thrust on this particular aircraft. So that concludes the entirety of the walkthrough. A lot of work went into this. Overall, I believe it was around 1,700 lines of code to complete all of this, and it allows for rapid iteration where the user can input different parameters to dictate different configurations of the aircraft and kind of define the design as they go. So it's a fairly powerful tool, but it is also limited to just fighter aircraft. So a lot of the equations are tailored specifically for that specific type of aircraft. For instance, the empty weight components or the approximations for the avionics, what type of avionics, what type of payload, empty weight fractions, all of those different parameters are dictated by the type of aircraft that this is. So unfortunately, it wouldn't be able to be expanded to, say, designing a transport aircraft. However, a similar structure in the code and also a similar mentality in how it is laid out and designed and developed in terms of the code itself. By simply swapping out different formulas, now that you have a framework, you could generate that a lot faster. And then if you put all of those together, you could have an actual integrated tool that would be able to not only change different parameters for the type of fighter jet, but also to change the different type of aircraft, and then change those different parameters around. So say now we have a transport aircraft with a short fuselage versus one with a long range for longer flights compared to a regional jet. So those are all some of the capabilities that are offered in the future if this tool were to be expanded. All right, thank you for watching. I know it's been a long video, but I hope you've enjoyed it.